Hello everyone, welcome to this video. In this video, we shall see what are half-range sine series and cosine series. So in the previous video, we have studied about the Fourier series expansion of any function, which was given by this expansion. Say fx was our function, then the expansion of this function in the interval, say alpha to alpha plus 2l, it was represented by the series a0 by 2 plus summation n varies from 1 to infinity a n cos n pi x upon l plus summation n varies from 1 to infinity b n sine n pi x upon l. So this was the Fourier series where these coefficients are represented by the integral formulas which we have discussed. So now, but in sometimes in various applications, the series is only required to be expanded in terms of either purely sine terms or purely cosine terms. So this is done when we extend our given function. Suppose the function is given to be in this interval 0 to L. So what we do, we just expand this interval, say from minus L to L, such that the function becomes odd or it becomes even. So if the function becomes odd, we have the sine series, and if the function is even, we have the corresponding cosine series. So let us see how it appears and why this is so. So suppose a function is defined over this interval 0 to L. Please note that the interval here should be half interval. So we assume the function is defined over this interval, then it can be extended into sine and cosine series by using these two forms. First is, if the function is given to be integral on the interval minus L to L, then if the function is even, then its Fourier series may contain only cosine terms. This we have seen in the previous video where we have discussed these two cases, when function was even and when function was odd. So in this case, when function is even, we have cosine terms and the coefficients are given by a0 is given by 2 upon L integration from 0 to L f of x dx. This is because fx here is even, and we know the integration of any even function from same limits to same limit, that is 2 times of that function where the limits change from 0 to L. So that even function, right? So this is the formula. So we use this formula here. So accordingly, a0 becomes 2 times limits changing from 0 to L. Similarly, an also becomes 2 times where the limits now change from 0 to L f of x cos n pi x upon L dx, and bn in this case is 0 because the formula for bn involve 1 by L minus L to L integration of the function f of x into sine n pi x divided by L dx. Now this is given to be even function, this is an odd function, so their multiplication is again an odd function. So we know the integration of any odd function from negative of same limit to the same limit is equal to 0. So this quantity bn is 0 when we have the function as an even function. Moreover, the Fourier series now then becomes a0 by 2 plus summation n varies from 1 to infinity a n cos n pi x upon L. So now you see here only we have the constant terms and we have the cosine terms. So this is the half range cosine series. So next, let us discuss the case of half range sine series. In this case, your function should be an odd function. So if your function is odd function, then the Fourier series will only contain sine terms. This we already know, and in that case the formulas a0 becomes 0, an becomes 0, because the formula for a0 was 1 by L integration minus L to L f of x dx. Now because fx is an odd function, so this integration is clearly 0 using the same argument, and an, that is given by 1 upon L integration minus L to L f of x cos n pi x upon L dx. So now this is an even function, this is an odd function, so their multiplication is an odd function, and this is eventually equal to 0. So this quantity is also equal to 0, and we have the formula for Bn as 2 by L integration limits from 0 to L f of x function as such, and then the sine terms dx. And the Fourier series in this case becomes the only containing only the sine term. So this is the half range sine series. So how this is done? How the function is made even and it is made odd function. Now let us consider an example. Suppose they are asking what is the half range sine and cosine series of f of x is equal to x, which is defined over this interval 0 to pi. Now your interval is 0 to pi, and you are asked find the half range sine and cosine series of this particular function. So now if you see this function here in this interval 0 to pi, you will say okay, f of minus x is equal to minus x, so which is equal to minus f of x. So I can say my function is an odd function in this interval. But what if I talk about this interval minus pi to pi? So in this particular interval we can extend our function. So from 0 to pi it is given to us that the function's value is fx is equal to x. So now we can extend this particular function. For the sine series, we want our function to be an odd function. We want fx to be an odd function. How this is an odd function? If we take the reflection of this particular function about origin. So about origin, suppose if this is the point minus pi, so if we take its reflection about origin, so your function would something be like this. So now you can say in this complete interval minus pi to pi, your function behaves as an odd function. So we have to do a construction over here to make our function as an odd function. So what we have done, we have taken its reflection along origin and we have extended it from 0 to a 0 pi interval to minus pi interval such that it now behaves as an odd function. So if we have an odd function, we know its Fourier series is given by this expansion containing only the sine terms. So you also see we save a lot of calculation over here. Moreover, these coefficients Bn, they are calculated using this formula. So let us calculate that for our given function f of x is equal to x. So if f of x is given to be x, so we just have to perform this integration. We can apply the by parts rule over here. So first function as such, then the integration of second function, then negative sign, the derivative of this first term, the integration of this second term, and so on. So that would be the result, and the limits will be from 0 to pi. When you substitute the limits and you solve, because you know the value of cos n pi, that is equal to minus 1 raised to power n, and you know sine n pi, that is equal to 0, and sine 0 is 0. So ultimately you have Bn as 2 into minus 1 raised to power n plus 1 divided by n. So this is the value of Bn that we have obtained. So we can substitute this value back into our Fourier series expansion, this one. So we would have fx is equal to summation n varies from 1 to infinity the value of Bn into sine nx. So we can just put the values of each n. So we would have an infinite series of this form where this 2 being constant could be taken out of the summation. So 2 is out. And then we have sine of x. When n is 1, we have sine 1x by 1 and minus 1 raised to power 2. So it would be positive sine 1 by 1, sine 1x by 1. Then we have when n is 2, we have here the power as 3. If the power is 3, it would be an odd power. So it would be minus here, sine 2x divided by 2. Again for 3, it would be, the power would be 4, it would be even, so plus over here. And then we have sine 3x divided by 3 and so on. So this would be the half range sine series of the function f of x is equal to x defined on the interval 0 to pi. So now the next thing to do is we can find the half range sine series of this particular function. Half range cosine series of this function f of x is equal to x. So for that, what we do, we create an even function for this particular expansion. So let us do that. Firstly, we'll make the coordinate system. Our function is defined from 0 to pi as f of x is equal to x, something like this. So now in order to make our function f of x as an even function, to construct an even function, what we do, we take the reflection of this function, we take the reflection of f of x about y-axis and extend our function, extend f of x from the interval 0 to pi to the extended interval minus pi to pi, such that f of x on this interval minus pi to pi would be an even function. So let us see how this is done graphically also. So this was our function from 0 to pi, right? So this was x, this was f of x. So now we extend this to this interval minus pi to pi also. So this is done by taking its mirror image. Suppose your mirror is placed over here. So you have some mirror placed over here. So if you take the reflection of this particular function into this mirror, you would have your function something like this. So this would be the mirror image of this particular function, right? Suppose this is the function. So now this function is an even function, and we know what is the Fourier series expansion of an even function. For an even function, you have f of x is equal to a naught by 2 plus summation n varies from 1 to infinity a n cos n pi x upon l dx, right? And what is L here? L here is basically pi. So we do not have to write this pi by L formula. So we can simply drop it, or we can put the value of L is equal to pi. So we would have a naught by 2 plus summation n varies from 1 to infinity a n cos nx, where what is this a naught? So firstly we will calculate a naught. It would be 1 upon pi integration from 0 to pi, right? And it would be 2 times pi because we now have an even function. So it would be 2 by pi integration from 0 to pi, the value of function dx. So it would be 2 upon pi integration 0 to pi x dx. And what is the integration of x? It is simply equal to x square by 2. And limits from 0 to pi. So this and this cancels. You will have pi as the value. So now next let us calculate an. An would be calculated using this formula: 2 upon pi integration from 0 to pi f of x into cos nx dx. So now your function here is x. So we would have 2 upon pi integration 0 to pi x into cos nx dx. So we just have to operate by parts here to calculate this integration. So it would be first function as such, the integration of second it would be sine nx divided by n, then minus integration or minus the derivative of this one, that would be 1, and then the integration of this one, that would be sine nx divided by n. I'm sorry, the integration of this particular function, so that would be minus cos nx divided by n, and we have the limits from 0 to pi. So we can simplify this expression. So we would have 2 upon, and it would be n square because 1n is due to this one and 1n is available over here. So we would have, when you substitute pi over here, so you would have x in place of x we would substitute pi by n sine n pi, and then when you substitute 0 you have 0, and then this minus and minus becomes plus, so plus 1 by n square into cos of n pi minus cos of 0. So we can simplify this 2 upon pi as such. Then sine n pi is 0, this term is also 0, this is 0, this is 0, so we are left with 1 upon n square. Cos n pi, that is minus 1 raised to power n, and cos of 0 is 1. So this is the value that we obtained after simplification. So this is our an. So we can substitute this value of an into our Fourier series. So our Fourier series fx would be, so f of x would be a naught by 2. What was a naught? A naught was pi. We just calculated this. So it would be pi by 2 plus summation n varies from 1 to infinity. The value of an. An is this one, 2 upon pi and then 1 upon n square minus 1 raised to power n minus 1. This was our an into cos n x. So this is our half range cosine series. So you can expand this series and you can write the infinite terms. So that would be this for this video. I hope you understood this concept. This was a pretty simple concept of half range sine and cosine series. So that is it for this video. I'll see you in the next one.